Okay, good morning. This is week 9. Time flies. So today we're going to look at examples of combined loading. Then I have a lot of questions on homework number 6, especially question 2, 3, and 4. I will attempt them. Okay, I don't think it's that difficult. Okay, once you use the technique that I apply. The solution manual that I posted online, the solution is not done by me, it's done by the publisher, okay? So sometimes their approach are different and I don't know why also, okay? But if you follow the technique that I teach, the answer will be the same. Now the announcement I'd like to make is the formula sheet for term test will be available today at 9 p.m. Okay, so you get to see your formula sheet. Okay, so the first example I'm going to do is I'm going to continue with our example over here. And we are going to look at stresses at element B now, okay, which I'm highlighting, the yellow highlight that I'm pointing you to. Okay, so we want to look at the stresses at point B. And usually the normal stress is usually very easy, okay? So this data that you see where axial load, sorry, this is not Px, this is Pz. Okay, so the axial load, I've taken all this information from our lecture last week on Friday, where you have minus 100 times 10 to the power 3 Newton. You got moment at about y-axis at 9,600. Moment on x is 22,750. Shear stress in x direction is 16 kilonewton, and shear force in the x direction is 16 kilonewton, and shear force in the y direction is equal to 25 kilonewton. Okay, so as I say, normal stress is the easiest thing to do. So I'm going to bring this image across. So element B is over here. Okay, so I'm going to draw element B. So at this position is our element B, and I think they have it in small b. So from here, we're going to calculate the normal stress. Okay, normal stresses acting on element B. So I'm going to write up the formula. So we're going to calculate stress in the z direction. Okay, so Pz over A. Now I don't know whether is it plus or minus yet until I refer to our equation. So we have m x over ixx multiplied by y, and my over iyy multiplied by x. Okay, and we are aware that the axial load along the z-axis will induce minus 500, as you can see over here. So we know that this will be a minus. Okay. Now moment about x is 22,750. However, the elements is at the neutral axis. Okay, so if you look along the x-axis, right, the element is on the neutral axis, so there's no y distance, so this is equal to 0. Okay, because the y value is equal to what? 0. Okay, so this term basically can be struck out. And then moment about y is going to be in tensor. Okay, so if you review the notes or the lecture on Friday, we did say that the moment in Friday, Eugene, come on. the moment. Okay, go on. So we did analyze here. So this is last Friday. I'm looking for moment at Y. So the moment at Y on element B is tensile over here. Okay, so we have this last week. So it's positive. Okay, so it's positive. So that's why I put a plus down here. Okay, so now we just plug in the numbers now. So this will be equal to minus 100 times 10 to the power 3 divided by the area. We just go to the table, look at the area, 5320. So it's 5320 times 10 to the power 6, minus 6, sorry. Plus by moment in Y, this is equal to 9600 divided by IYY again. You go back to the table to look for the IYY value, 9.03 times 10 to the power minus 6. Now is the x distance. That's where we have to be careful about this x distance, right? So if you see the x distance is this is the direction, right? X direction. So the x distance is equal to TW, the thickness of the web, divided by 2. So thickness of the web is 7.24 times 10 to the power minus 3. You divide by 2. Okay, let me check again. 7.24 times 70. Yep, that's it. Okay, so the normal stress is equal to minus 100 power 3 divided by 5320 power minus 6 is equal to minus 18.797 times 10 to the power 6 plus 9600 times by 7.24 power minus 3 divided by 2 divided by 9.03 power minus 6, 3.84 9 times 10 to the power 6. So the normal stress is equal to minus 14.984. Sorry, 948 times 10 to the power 6 Pascal. As I say, this is always the easiest. The normal stress is easiest, okay? So next we come, we're going to do the shearing stress. Okay, we're going to look at shearing stress. Any questions so far from anyone? I don't hear. How about live? No? Okay, so we are going to calculate the shearing stress. Induced by Vx, which is equal to 16 times 10 to the power 3 Newton. Okay, so I'm going to copy this image here. So Vx is coming in by 16 times 10 to the power 3 Newton. Okay. So when we construct the shear flow, these are all thin walls. So I'll highlight down here using or analyze with thin wall, white flange. Right, it's not a box beam at all. Why we call it white flange? Because we have, for now, we have 4 different terminals. So the shear flow will flow this way. Okay. Right. So like what, just to recall, the web controls the direction, yes or no? Right? So when it reaches to the flange, you go to the center. Okay. And over here, the dot I just draw in pink at the center, I'm going to circle it now. This is where our element B is. Right? And if you look at two arrows coming together, right, in different direction, they cancel out one another. Right? So at element B is also one of our terminal. Right? So for this case, the shear stress, and we realize that it's in the Z plane, Y direction is equal to 0. Why is it equal to 0? Because it's a terminal, element B. Is at the terminal. And you also realize that Q, first moment of area, is also equal to what? 0. Okay, because it's at the terminal. Terminal, always at the terminal, the first moment of area is equal to 0. Like you see over here, this is a terminal, 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 terminal. First moment of area is equal to 0. Okay, so that's where it's interesting, right? You have a shear force of what? Of 16 kilonewton, but the shear force, that shear force induce a shear stress which is equal to 0. Okay, so if you're going to pick an argument with civil engineers, you can tell them we can have a force, a shear force, and also it's possible to be equal to what? 0. Okay, it's not just on normal stress at the neutral axis is equal to 0. Shear force is also equal to 0 if it's at terminal. So that is our Vx. But before I go on, if we were to write out the formula, right? Shear Zy is equal to shear Yz. And this is equal to Vx over Iyy, right? Qy divided by T. Why I did this? Because I did not know the moment is about the y-axis. Okay. So for this case, this is equal to what? 0. Okay. Then the next one we're going to look at is the shear stress. So far, anyone, any questions so far? Okay. I hope I'm not going too fast on a Monday morning today.
Yeah, one quick question.
Yes.
So that's shear ZY because the shear flow is in the Y direction?
Yes, it is.
Okay, thank you.
You got it there, look. Okay, so the next one, I'm going to copy this whole thing. We are going to determine the shear stress due to Py, right, where it's equal to 25 times 10 to the power 3 Newton. Okay. So when you look over here, we are we're going to use thin wall analysis. White flange. Like what I taught you guys, white flange is always just Q. Okay. So now we are going to look at Vy. So Vy is coming in at 25 times 10 to the power 3 Newton. Okay. Then we construct the shear flow. Now it's different, right? You have to be really, really careful. So now this is where I just drew the dot. This is the point of interest. for our element B now. Okay. So our shear stress now, right? Our shear stress is Z plane y-axis. Okay, or the shear flow is acting in y direction. So this will be equal to Vy over Ixx, right? Qx, first moment of area about the y-axis, about the x-axis, divided by t. Okay. So once you write out a formula like this, you tend to panic. Okay, don't panic. Okay, write down what we know. I mean, not you. I will get panicked. Okay, so Vy is equal to 25 times 10 to the power 3 Newton. Okay. Ixx